In this video, we're going to prove a very important result about groups of order p squared, where p is a prime. And that result is the following theorem. Every finite group of order p squared, p a prime, is abelian. So previously we had shown that every group of prime order is cyclic. We can't go quite that far with groups of order p squared because we know, for example, that a group of order p squared could be z mod p squared, or it could be zp direct product zp. I'm using the symbol O+. That's a symbol that's commonly used for direct products of abelian groups. And we'll see that more and more as time passes. We'll see this symbol rather than the X symbol. Okay, so these are both groups of order p squared. They are different because this has elements of order p squared, and every element over here has order p. Therefore, this group is not cyclic. So that's why we can't say that groups of order prime squared are cyclic, but it is going to turn out they're all abelian. Okay, so anyway, how do we prove this? Well, first we're going to prove the following lemma. And the lemma in itself is kind of a major deal. It's a major result. The lemma is that every group of order p to the k, where p is prime and k is greater than or equal to 1, has non-trivial center. And the way that we're going to prove that is to use the class equation. That is the equation that represents the sizes of conjugacy classes. We're going to use the class equation. So the class equation, just as a reminder, is that if I have a group G of order p to the k, p prime, and k greater than or equal to 1, then by the class equation, I know that the size of the group G, that is the number of elements in G, is equal to the size of G's center. Remember, that's the collective size of all of these singleton conjugacy classes, plus the sum over all other conjugacy classes of the order of G divided by the order of the centralizer of an element of that conjugacy class. All right, so this is something that I know. And this, by the way, this seems like a really clumsy way to construct a summation. I just said sum over other conjugacy classes, when in fact I really don't know a whole lot about the other conjugacy classes. I don't know how many there are. I don't know how many elements are in each conjugacy class. All I know is that I have some other conjugacy classes here. Okay, but it turns out that's actually all that I need to know in order to prove this lemma. So here's why. Notice, if X is not in the center of G, then the conjugacy class of X must have more than one element. Must have more than one element. Well, how many? Well, the size of that conjugacy class must be equal to the order of G divided by the order of the centralizer of X. That's by the orbit stabilizer theorem. The order of G is p to the k. And the order of the centralizer of X, well, that's a subgroup of G. So by Lagrange's theorem, its order has to be something dividing p to the k. And furthermore, it has to be a proper divisor because if the order of the centralizer of x were just p to the k, well, that would mean that the centralizer of x is the entire group. And if x is centralized by everything, then x commutes with everything. That would mean x is in the center. And we're assuming that x is not in the center. So simplifying this just a little bit, what that means is that the size of that conjugacy class, the conjugacy class containing x, has to be p to the k divided by p to the l for some integer l that is at least 0, but definitely less than k, because if it were equal to k, that would mean that x is centralized by everything and belongs to the center. So what does that mean? Well, that means that my conjugacy class is going to have p to the k minus l elements. So the conjugacy class of x has p to the k minus l elements, and since L is less than K, that means K minus L has to be at least 1. Okay, so that means that the conjugacy class of X has some power of P elements, and that power of P has to be at least P to the first. A power of P elements, and more importantly, a multiple of P elements, because that power of P was not P to the 0. Okay, now when we get this deep into an argument, it's easy to lose sight of the big picture. The big picture is contained in this equation right here, the class equation. So again, what that's saying is the order of G, which by the way was P to the K, that's equal to the size of the center of G plus the sum of a whole bunch of other sizes of conjugacy classes, but each one of those is some power of P. I'm going to call it P to the m sub I, and then each m sub I is at least 1. And then what are the i's? The i's just go from 1, 2, 3 up to the number of non-singleton conjugacy classes, if that makes sense. So just as a reminder, some conjugacy classes are absorbed over here. The singletons are all over here because a singleton conjugacy class is just an element of the center. So these are all the other conjugacy classes, and each one has size a power of P that is at least P. Okay, but wait a minute. We have this number here, this P to the K, is equal to this sum of multiples of P. These are all multiples of P, plus the size of the center. But certainly P divides this number. We're assuming, of course, that K is not 0, so this is a multiple of P. So P divides the order of G, and P divides all of this. I'm just going to say P divides all of this. So that means P has to divide this in order for this equation to work out. So P must divide the order of the center of G. And if P divides it, well, we know the center of G has to contain at least the identity. So that order has to be at least 1, can't be 0. So P divides that. That means that the center must have some number of elements that is a multiple of P. Has to have more than just the identity. So this can't be just the identity. So I think that proves our lemma here. Let's just zoom out and make sure we've proven what we wanted to prove. So our lemma was every group of order P to the K has non-trivial center. That was way too much zooming out. Let's try that again. And I think we've proven that. So let's check that off. Great. So what about our main theorem? Every finite group of order P squared is abelian. I claim that this is actually just a couple of steps now. So let's just move up to where we can work up here. Okay, so here's the proof of the theorem. All right, well, let's assume the order of G is p squared, p a prime. So now the question I'm going to ask is, how big is the center of G? Okay, because I think there's three options. Because I know that the center of G has to be a subgroup of G. That's something we've proven. The center of G is definitely a subgroup. So by Lagrange's theorem, we know the order of Z of G must divide p squared. And I know of three divisors of p squared that could be the order of a group because they're positive integers. This must be 1 p or p squared. Okay, so let's just knock out as many options as we can. Well, first of all, I claim this can't be 1. And that's by our limit that we just proved. This is since Z of G can't be trivial by the lemma. We've proven that the center has to contain something by the identity for a group of order a power of a prime. All right, what about P? Also, I claim that the center can't have order P. And this is because if it did, then think about G mod Z of G. We know that the center is normal, so we can certainly mod out by it. Well, this would be equal to p squared over p, order G over the order of the center, which would be p. So this quotient would have to be cyclic because its order is prime. Okay, but we know that G mod Z can't be cyclic other than the identity by the G mod Z theorem. So G mod Z of G can't be cyclic of order G, or order P. So that's a contradiction as well. So we know that the center can't be just one element, can't be just P elements. So what does that leave? Therefore, the order of the center has to be P squared. And thus, the center contains every single thing in G, which means G is, after all, abelian. So that's pretty cool. We've shown that every group whose order is p squared has to be abelian, where p is prime. Not necessarily true for p to the third or p to the fourth, but definitely true for p squared. We also know by the examples we talked about earlier, the ones I'm drawing in this blue box here, that a group of order p squared does not have to be cyclic, but it will have to be abelian. And one thing we'll show later on is that if you're abelian and your order is p squared, these are the only two options. So those are the only two possibilities for a group of order p squared.